Part E, merge sort, another sorting algorithm. So this one also very useful. Yeah. So after merge sort, then quick sort. So on Wednesday we will learn quick sort. Yeah. So next week I like to talk about another sorting algorithm. So the last one. Yeah. Yeah. So this week 2 sorts. E.1, introduction to merge sort. Yeah. First, let me talk about why we need to learn another. Yeah. So far at this point we have learned several. Yeah. Selection sort, bubble sort, insertion sort. Yeah. So then merge sort, quick sort next week. Yeah, actually 2 sorts next week. Heap sort and counting sort. So total 7 sorts. Yeah. All right, so this one, number 4. Yeah. First, let's look at a basic computing problem. Yeah. Just to merge 2 sorted arrays. It's a simple computing problem. Yeah. But this is a key step of merge sort. If we solve this problem, pretty easy. After we solve it, then the merge sort, we just do the recursion. So each iteration, we apply this merge operation. Then we're done. Yeah. So that's simple. Yeah. All right, so let's look at a question. Given 2 ordered arrays, the question, how to merge them to get an ordered array. Yeah. So you're given, the data you're given, 2 arrays, but they are both ordered. So you can take advantage of that information. Yeah. Because we can do much better if we have ordered data. Yeah. Now, can you find the fastest possible algorithm to merge them to get one overall ordered array? Yeah. That's the question. Yeah. All right. Yeah. So, just a minute. Yeah, let me enlarge that screen. Although my recorded side, I record my screen. So that's the, projected screen, but I want to make it larger so you can see better. So here I choose full screen. I should choose full screen. Yeah. And minimize this. Yeah. So you can see larger. Yeah. All right. Yeah. Good. Yeah. Motivation. Yeah. So here I want to give you a very special situation. Yeah. Although it is rare to have this kind of situation in the real world, but sometimes we need to consider this special situation. So let me describe it. Yeah. Why we need to consider this problem. Yeah. So here, for the motivation part, actually there are two cases. Yeah, 2 cases. The first case, we prepare this merge operation for our merge sort. Yeah, so that's the first case. Second case, I want to describe a special real-world situation. Although you won't see it happen quite often. Yeah, it's rare. It's pretty rare, but it could happen sometimes. So let me talk about that special situation. Yeah. All right, the situation is like this. Now think about how to sort a huge array. How huge it is. Okay, here let me describe this. How huge it is. Yeah. So in the real world, we know right now it's in the big data era, right? Yes, here we are in the big data era. So you can imagine it's pretty common. The data you need to process could be, in large scale, huge scale. Yeah. In that situation, think about, in our computer algorithms, when we process our data, is it in general we need to load the data into our main memory? How do you process your data? Load the data into main memory, right? Yeah. So, if you look at inside, computer CPU processing, the first thing you need to load data inside main memory, then to do processing. Yeah. But think about how large is your memory size? Yeah. How large? There is a limit, right? Yeah. Here the laptop. Yeah. So if we talk about laptop, usually 16 gigabytes. 16 gigabytes. This one, I don't know, 16 or 8. Yeah, because when you order your laptop, based on the price tag, yeah, so you can choose 16, more expensive. Yeah, this one probably 8 gigabytes. Yeah, because at that time I tried to choose between 16 and 8 gigabytes. Yeah, but there is a limit. Yeah. Think about if your array is larger than that. Your array size. Yeah. Initially, you store your data on your hard drive. Okay. Yeah. So no problem. You can store your data in a hard drive. Okay. But now, when you need to sort it, let's assume the data size is larger than your memory size. How can you sort it? Yeah. So you need to solve this technical problem here. Okay? Yeah. So the title of this module, Divide and Conquer. Can we use divide and conquer to solve it? Yeah. We cannot load the whole set of data. Can we split our data into multiple subarrays? Each one we can load it. Each smaller subarray we can load it into the main memory. Okay? No problem. Yeah. If we do that, yeah, divide and conquer, split, yeah, load one subarray by one subarray. Every time we can sort one subarray. All right. So let me use a simple diagram to describe the situation. Suppose this line segment represents the whole array. And we cannot load this whole array into the main memory. Let's split it, okay? Divide and conquer way. Split into multiple smaller subarrays. And we can assume each subarray can be loaded into the main memory easily. Okay? After you load it into main memory, you can sort it, right? You run your sorting algorithm. You can sort it. So here we assume each subarray, we can make them ordered. Yeah. So after we process one by one, okay? After we go through all the subarrays, we get all these subarrays ordered. Next question, because our goal, we want to get the whole array ordered, right? That's our goal, okay? Now the question, to get the whole array ordered, do you need to solve this problem, number 13, that basic problem? Merge two ordered arrays. Yeah, so here, yeah. Although this won't happen frequently, yeah, but it could happen, especially when you process large amount of data. Yeah. So here, now we need to merge any two ordered arrays. We need to run our new algorithm to merge them. Okay? Yeah. So, yeah. Okay? Yeah. So you can follow any order, right? You can follow any order to merge them. Okay. Yeah. which order to follow. Yeah. Because you have many choices, right? Think about it. If here we have 4 subarrays, when you merge any 2 of the 4 subarrays, you have many different ways to merge, right? Yeah, yeah. But there must be one way that is the fastest. There must be one way, the fastest way. Okay? Yeah. So how to get the fastest way? Yeah. So I leave as a homework assignment question. Okay? Yeah. On Wednesday, I will give you our second homework assignment, number 2. Yeah. In that one, you need to solve merging multiple subarrays together. You have several different ways to merge. Which one is the fastest? You will do that. Okay? All right, so let's continue. Yeah. All right. And also, you can do parallel computing. Yeah. See, you have all those independent subarrays. If you have multiprocessors, you assign them to multiprocessors to do sorting in parallel, right? Yeah. So for parallel computing, yeah, you can make the whole sorting task faster. Yeah. So, all right, so here I do not go that much detail. Yeah. Let's continue our merge implementation. How to merge 2 sorted arrays, given 2 arrays that are already sorted. How to get a new sorted array that contains all the elements. Yeah. So here, because the order information is very important, so we have to take advantage of the ordered structure. No. You don't want to waste that special structure property. Okay? Yeah. But the question is how to take advantage of it. Yeah. So here, at this point, we have learned 3 sorts: selection, bubble, and insertion. Yeah. So when we need to solve a new problem, that's our experience. So we need to, get some idea from our old experience. Yeah. So which one can provide us some useful information here? Yeah. So let's look at that question. Yeah. Do not use any sort that does not make use of any order information. Let's think about in the selection sort. I hope you still remember the selection sort. Okay? Every round we apply finding the minimum, right? To place one element in place. That's our selection sort. Think about if you are given ordered data or unordered, any difference? Can you see any difference? For ordered data, unordered data, if you apply selection sort on it, is there any difference? Any difference? Yeah, let me see if Zoom student make response. Any difference? Ordered, unordered data for selection sort. Yeah. No difference. Because that number the same, right? Remember, that number is 1/2 times n minus 1. This many comparisons, no matter what data you have, you need to do this many comparisons. That's for selection sort. How about bubble sort? Same thing, right? Bubble sort, you need to do this many comparisons. No difference. Okay? Yeah. How about insertion sort? Can you see any difference? The data with ordered data and unordered data, the number of comparisons you need to use, see some difference? Insertion sort. What is the biggest property of insertion sort? Can you still? Most important property of insertion sort. That is, remember, if the data is almost sorted, it is extremely fast. Think about that, okay? So that's for the insertion sort. That is, if for the general unordered data, the insertion sort, so here, I'm talking about insertion sort. Okay? If the data, arbitrary data, you get big, so here, you get a big theta of n squared, right? If for ordered data, you get a big theta of n. Is it much faster? You get big theta of n. Yeah? From big theta of n squared to big theta of n. Big improvement. So that means we should borrow the property from the insertion sort here to help us make our merge operation faster. So what we are going to do, basically, we need to start from the insertion step. Because the insertion step can help us take advantage of the ordered data property. Yeah, okay? Yeah. Ordered data property. Yeah. So now, let's recall our insertion step. Yeah, because we want to modify the insertion step to do our merge operation. Merge operation. Yeah. So here, that's how we learn from experience. If you do not have any experience, it's hard, right? When you solve a problem, if you do not have any experience, you need to do everything from scratch. That's hard. Now we have a lot of experience. So the insertion sort, that's our experience. Okay? So let's take a look at the insertion. Yeah, here we plan to use insertion sort. Okay? Yeah. All right. Yeah. So because there is a nice property there. Okay? Yeah. Now let me use a simple diagram. So we try to, do the development here. Okay? All right. Why? Yeah, so here, when we look at the insertion step, we want to modify the view. Yeah. Because if you use the original insertion operation, it won't work because our situation is different. You have to modify it. We have to make it to a new version supporting merge 2 ordered arrays. That's a new problem. Yeah. All right. Yeah. But when you start, so let's look at this insertion step. Yeah. So we have a new element V. Yeah. Then an ordered array, whole array we assume ordered. So you need to insert V into an ordered array. That's the typical insertion step. Yeah. But here, we change our view slightly. Yeah. We change our view. Yeah. Can we treat this old insertion view, can you modify it to make a merge view? Yeah. Our goal is merge. So we want to adapt our view to the merge operation. That's the difference we need to do. Yeah. All right, so look at this this V, can we treat as an array, one element array? That element just one array, one element. Can we treat as ordered? One element, it is ordered. Yeah. So can you treat, this is a special case for the merge operation, merge 2 ordered operation. Yeah. This time one element, next time two elements. How about that? Then we grow the number, so multiple elements, yeah, we do the merge. Yeah. So that's, so it's sorted, yeah, both sorted, ordered, yeah. Yeah. All right. So our new view, merge view, okay, yeah. Merge two sorted arrays for a new sorted array. Yeah. Okay? The question, detail. Yeah. The detail, if you recall our insertion operation, pretty close to the insertion operation. Yeah. But we only need to do the necessary modification for the merge case. Merge case. Okay? Yeah. Yeah. So that's the value of our old experience. So now, at least we can see some, rough target. Okay? Something, we can envision, right? We can envision. Yeah. Yeah. So not in a blind situation, right? At least, we know we should go that way. Okay? Yeah, not blind. Yeah, so, yeah. All right. Yeah, so here we merge two ordered arrays, one size k, another size 1. Okay? Yeah. Yeah. But these two arrays not balanced. Data distribution is not balanced, right? Data distribution is not balanced. Yeah. And we know, last time I talked about balancing principle. When you distribute your data in an unbalanced way, then you will get a worse performance, worst efficiency overall. Yeah. If you distribute your data evenly, then close to the best case. Yeah. Close to the best case. That's our, what we learned, balancing principle last time. Yeah. To improve performance for the worst case, we want to apply balancing principle here. We try to split the array as even as possible. Yeah. When you do divide and conquer, you have freedom to make the split, right? Yeah. When you do divide and conquer, you have freedom to choose how to split your data. So we split the data as even as possible. Okay? Yeah. Try to make two subarrays of equal size. Yeah. If all the number of elements, one subarray is has one more element than the other. Yeah. As even as possible. Yeah. Now, merge operation. Now, let's work on the merge operation. Yeah. How to achieve balanced subarray. Here I use a simple diagram to show you how to split our data as even as possible. Yeah. Idea. Whenever we merge two subarrays, we make them of equal size, we split them as even as possible. Yeah. Here, let me use a simple diagram to show you. Yeah. So here, let me use this line segment to represent the whole array. Okay, yeah. The first time when we do the split, yeah. So let us split in the middle, right in the middle. Yeah, yeah, yeah. So the midpoint. Yeah. Then next time, two subarrays, another round, splitting in the middle. Yeah, another round. Keep splitting like this. Yeah. And at some point, we have to stop splitting. We cannot split forever. Yeah. Yeah. So think about when each file contains one element, you have to stop splitting. Yeah. after you stop splitting, then we do the merge operation. Merge two adjacent subarrays. Yeah. So here, yeah. So let's assume we merge two adjacent subarrays. Yeah. So we go opposite direction after the split. So now let's go, backward. Yeah. Merge two adjacent. Then another round, merging two adjacent subarrays. Yeah. Yeah. And we get a larger ordered subarrays. Yeah. Every round, we get a larger ordered subarrays. Yeah. So another round, larger. Yeah. The final round, we need to merge two ordered subarrays. So we get a whole array ordered. Yeah. So here you can see if you figure out how to merge two ordered subarrays, you can use this kind of recursion. Yeah. So you implement by recursion, yeah. So you can sort the whole array easily. Okay? Yeah. So the only thing we need to do, merge two ordered arrays. That's all we need to do. Yeah. Yeah. All right. Yeah. So later we will do analysis. Yeah. So actually, in this way, yeah. Here, the balancing principle gives us some confidence. Yeah. Because here, we split our data in a balanced way, so that balancing principle gives us confidence. Yeah. We should, in this way, we should avoid worst case performance. Yeah. Okay, yeah. All right. Yeah. So next, we need to study the merge step. Next one. Yeah. Here, let me use diagram to show you. Yeah. So we have two ordered subarrays. Let's merge these two ordered subarrays by doing comparison. Yeah. So yeah. This comparison way modified from the insertion operation. Insertion. Yeah. All right. So, yeah. So let me remember insertion operation. Every time when we compare our given key with one element in the ordered array, we can put one element. Yeah, so insertion. Yeah, actually. Yeah, yeah. So that's slightly different. So here. Yeah. So here. All right. When we start, let's take the smallest elements in these two subarrays first and make the first comparison. Yeah. So you get a smaller one and a larger one. Okay? Yeah. So let's make this min 0 as the smaller of the two elements. The smaller one, what can you say about the smaller one? After our first comparison, can you say something about the first one? After the first comparison? Yes. If it's the minimum of all the elements, can you put it in place? Yeah. Yeah. We know. Yeah, we can put it in place. Yeah. So here, let us create a destination array. Yeah. Destination. Yeah. So let me draw this. Yeah. We have a sequence of empty locations as the destination array. After first comparison, we can put one element in place, drop it in this destination array, okay? Min 0. Okay? Then the larger one, max 0. Max 0, we cannot say it's in place, right? Yeah, you cannot say it is in place. So you need to do another comparison to see if the max 0 is in place. Yeah. Here, let's assume the max 0 is this B0 element. Yeah. There is another case, A0 case, right? Yeah. But here, let's just we only need to look at one of the two cases. Now, let's assume the B0 case. If max 0 is this B0, our next comparison we should do, we compare A1 and B0. Yeah. Then you have mean 1 of A1 and B0, mean 1. Yeah. So what can you say about mean 1? Second minimum, and it must be in place, right? Yeah. So we put mean 1 in place. Every time, so you know, every time when we do one comparison, we can put one element in place, right? Yeah. Yeah. So, yeah. And sooner or later, we can put all elements in place, right? Yeah. If we put all elements in place, have we sorted the whole array? Yeah, we sorted all. We sort the whole array. Yeah, that's the whole idea. Okay, yeah. All right, so we keep doing. That's the whole idea. But then the question is, we want to look at the best case and the worst case. Let's look at the worst case. Yeah. Because definitely we have many different cases, right? Think about what's the worst case here. Yeah, alternating. Yeah, yeah. Because you need you need to do all the possible comparisons until you reach the end. The last one, you don't need to do comparison. When you have a single element, you don't need to do comparison. Before that single element, when you have two elements, you still need to do one comparison. That's the worst case. Okay, so you do not finish. Yeah, because sometimes you can stop earlier, right? You can stop earlier. Yeah, in this way, yeah, you can stop earlier. Okay, yeah. But on the worst case, we stop at the latest point. Latest. Yeah. So that means we still, when we determine second to last element, we still need to do one comparison. Okay? Can you, based on this understanding, can you see how many comparisons we need to do? Yeah. Suppose first array we have k element. Second array we also have k element. How many comparisons do you need? 2k minus 1. Yeah. Total elements 2k. But you don't need to do the last one. You don't need to do. Other than the last one, every one element, if you want to put it in place, you need to do one comparison. 2k plus minus 1. Yeah. All right. So that's the conclusion. For every new mean added, we may need one comparison except the last one. Yeah. Yeah. So the normal comparison for the worst case, here, 2k minus 1. Yeah. Or we can understand in this way. The total number of elements minus 1. That's the worst case. Okay? Yeah. Yeah. Now, we want to consider worst case for the general case. What's the general merge step? This time, we do not require A subarray, B subarray have equal number of elements. A subarray, there are n elements. B subarray, there are n elements. The number could be different. That's the general merge step. Yep. In the real world, we may need to merge, do the general merge. Okay. Now the question for the worst case. How many comparisons do we need? Based on the previous slide. How many comparisons? What's the formula? Correct. M plus n minus 1. Yeah, total number of elements minus 1. Total number m plus n. Okay? Yeah. So we get that formula. Worst case, m plus n minus 1. Worst case. All right. Now, best case. So we get the worst case result. Next, we want to do the best case. Question. Now, This time, we want to minimize the number of comparisons. Can you use your imagination in your mind how to minimize the number of comparisons?
Compare the minimum of 1 to the maximum.
We still do this same kind of comparison, the same as the older way, okay? Same as the older way, yeah. Yeah. But think about for what data situation. Yeah. The only difference is the data could be different. For what special data situation you get a best case. You do not change the comparison format. Comparison, we still use the previous, same way. Okay? We don't change. Yeah. But now, think about, so here, let's imagine this situation. Think about if B0 has the value, it is greater than all the elements in the A subarray. Greater than all elements in subarray. So B0 can beat all elements in A subarray. What would happen? Yes. So when you use B0, compare with each one in the A array, you put them in place. After that, you don't need to do more comparisons, right? Yeah. For the remaining B elements, you know they are greater than B0. You don't need to do any comparison, okay? Yeah. So you put them in place automatically. Yeah. So that's for the best case, right? Yeah. So based on that analysis, the strategy, we try to exhaust one of the two subarrays as early as possible. Okay? You have two cases. The first case, you use B0 to exhaust all the elements in A subarray. Yeah, the first case. Second case, you use A0 to exhaust all elements in B subarray. That's also possible, right? Yeah. Yeah. So which subarray is shorter? Yeah. Yeah. So here, think about, because we do general case. The first subarray, there are n elements. Second subarray, we have n elements. And you don't know m smaller or n smaller. You don't know which one's smaller. Yeah. So can you tell me, based on this analysis, what should be the formula for the best case merge operation? M and N. Which one? Minimum number comparison. Minimum number comparison.
Is it n plus n minus 2 over 2?
Y plus, yeah. Because one element in the longer subarray can beat all elements in the smaller subarray. So what do you need to do? Only the number of comparisons, the same number as the elements in the smaller subarray. After that, you stop. After that, you stop. Okay? Yeah. The minimum of M and N. The minimum of M and N. Yeah. Yeah. So you assume you use an element in the longer subarray, the smallest one in the longer subarray, it's already enough to beat all elements in the shorter subarray. Then you are done. Okay? After the minimum of this many comparisons, yeah, you put all the elements in the smaller subarray in place. After that, the remaining elements all in B subarray, you know, they must be in place. They must be in place automatically without any comparison. Okay? Yeah. So that is, you only need minimum of M and N number of comparisons. That's the best case. Okay. So after you have, you know the worst case, you know the best case. Yeah. Other cases between these two numbers. Yeah. Other cases between these two numbers. Okay. Yeah. All right. So now, efficiency analysis for the merge sort. So at this point, we know the merge sort, we have a quite different sorting algorithm than before. Yeah, this is a new sorting algorithm comparing with the previous three. Yeah, quite different. Yeah. Now we want to see if we run this algorithm, let's say for the worst case, what is the growth function of this growth function? What is the growth function of this merge sort? Yeah. So in this E.3, we want to get that. We want to find a way to estimate the growth function for the merge sort. Yeah. All right. Yeah. Derive recurrence relation. Yeah. In order to estimate the growth function, we need to derive the recurrence relation for the merge sort. Yeah. All right. Yeah. It's pretty straightforward. Yeah. So let's estimate worst case efficiency. Yeah. All right. Given an array with n elements. Yeah. Here, remember, when we do estimate, we do not require our expression is very accurate. We can use approximation. If you want to use accurate representation, computation could be very hard. Yeah. But here we are doing computer science analysis. It's okay, we do approximation. Yeah. Yeah. So that would be much easier. Approximation. Yeah. Let us use this capital T function to represent total number of comparisons to sort the whole array by the merge sort. This T function. Yeah. Then we do divide and conquer, so we split this array, even split. Yeah. Each subarray half size, half of the original size. So that's our two subarrays of equal size. Yeah. Approximately equal. Yeah. All right. Yeah. Then conquer, when you conquer it, you sort each subarray by recursion. Yeah. Yeah. By more recursion. Okay? Yeah. Yeah. So then, if you sort each subarray, how many comparisons? What is the representation for the number of comparisons to sort each subarray? Yeah. The size, half size, n over 2, half of the original size. And you use the capital T function, T of n over 2. Yeah. Second one also T of n over 2. Yeah. That's the recursion cost. Yeah. So you apply, you do the recursive function calls twice. Okay? The first time, second time. First time, T of n over 2, number of comparisons. Second time, another T of n over 2 number of comparisons. Okay? But not done yet. After you conquer each subarray, you need to do more work, right? You need to merge them. You need to merge two subarrays. The merge cost, what is the merge cost you need to do? Okay? Total number of elements minus 1, right? Yeah. Total number of elements minus 1. Yeah. 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 Can we approximate use n comparisons? Yeah. The accurate, precise number is n minus 1. Yeah. But we use approximation, right? We use n as its approximation. Yeah. So here, to make our formula as simple as possible, we use n. N number of comparisons. So now we get our recursion formula, T of 1 equals to 0. one element, no comparison. So T of 1, 0. T of 2, one comparison to get it ordered, right? Sorted, one comparison. So initial values, these two simple initial values. After that, we have our recurrence relation. T of n equals 2 times T of n over 2 plus n. Plus n. Okay? Yeah. So our next step, we need to use this recurrence relation to help us estimate how large is the t function. How large is the t function?
Where do you get plus n?
Plus sign? What?
Where t of n is 2t n over 2 plus n. Where does the plus n come from?
Plus.
So it
Yeah.
says 2t n over 2 plus
Right.
n. Where does the plus n come from?
Merge. When you do extra work, do you need to plus further number of comparisons? Further number? Yeah. Merge number of, yeah, so here let me write. Number of comparisons used for the merge step. Merge step, there is a cost, right? Yeah. You have two order array, after you combine them, you need to apply standard merge operation. That's the worst case. Here we use the worst case. Yeah. Best case, you use n over 2. Best case, you use n over 2. Yeah. So just modify n over 2. Yeah. All right. Yeah. Now, our next question. We want to solve this recurrence relation, but if we want to calculate it in a rigorous way or in an accurate way, it could be very hard. No? It could be very hard. Now, we want to estimate. We use some simple way to estimate it. Yeah, that won't be very hard. So here I want to introduce a special simple way to estimate. The approximation actually pretty good. Approximation is pretty good. Yeah. All right. And another way, yeah, some people, yeah, because there is some theorem in our textbook, in the appendix. Appendix, you can find the theorem. We apply that theorem, then you get this t function representation quickly. Okay? Yeah. So that's, mathematically, you can apply a special theorem in our appendix. Okay, yeah, so that's another way, all right? Yeah, but here I like to introduce a very smart, simple estimate method called a recursion tree method. Recursion tree, yeah, here we have a recurrence relation. We want to draw a binary tree corresponding to the implementation of this recurrence relation. So we call it a recursion tree. Yeah. Then we use this recursion tree, we can estimate the total implementation cost to implement this recurrence relation. We can also get a similar estimate. Yeah. Let me talk about that recursion tree. Yeah. Yeah. Here, the simpler case, here I, in our discussion, in order to make our discussion relatively simpler, here we consider n equals power of 2. Power of 2. Yeah. But later, we do not need this assumption. Later, yeah, because we're doing estimate. Yeah, we're doing estimate. So we can use fraction formulas. Yeah. We don't require our fractional representations corresponding to integers when we do estimation. Yeah. All right, so here, let us assume n is power of 2, so we can rewrite our recurrence relation in this way. Yeah. Recurrence relation in this way, power of 2. Yeah. Okay. Pretty simpler. Yeah. The question, can you solve this new recurrence relation? Yeah. Because it's much simpler. Yeah. You can do this kind of recurrence relation round by round. The second round, third round, keep going until you reach the bottom level using the base cases. Yeah. So the next round, yeah. All right, so here, we do not list all the details. Yeah. Let's just use a special transformation method, division method, to transform this formula. We do division, both sides. Yeah. So what special division? Yeah, we do division with divisor 2 to the k, both sides, division. Yeah. Yeah. After you do division, you see the new representation, left-hand side, right-hand side. Are they similar? They have the same structure. They have the same structure. That's the goal. We do division operation here because we want to make the both sides, yeah, other than the constant number, both sides have the similar structure. Yeah. Here we get it, similar structure. Yeah. So let us introduce a new function to represent the structure. New function. Here we assume we introduce a new function, g of k equals t of 2 to the k over 2 to the k. New function. Because after the new function, yeah, the substitution method, yeah, our equation becomes much simpler. G of k equals g of k minus 1 plus 1. It's much simpler, right? Yeah. You greatly simplify the original recurrence relation. This is the original recurrence relation. Yeah. Still not that simple. Yeah. But this version much simpler, right? Yeah. You can keep doing iterations like this. Yeah. Yeah. The next round, yeah, your initial value when g of 1 you plug in equals t of 2, right? Yeah. So g of 1 equals t of 2 to the 1 to the first, t of 2 over 2. So that's 1/2. T of 2 equals 1. So 1/2. G of 1 is 1/2. Okay? Yeah. So the next iteration equals g of k minus 2 plus 2. Yeah. Yeah. Plug in. Yeah. Keep doing this, yeah, until you reach the bottom. The bottom, this side, we want a g of 1 here. And how about plus? How about this number? G of 1 plus what number? Can you get that? G of 1 plus what number? The question mark. Which number we should put there in that question mark place? Yeah. Yeah. Remember, we talked about a concept called invariance concept in our early class, right? Do you get the idea? Invariance concept? Yeah. Here, we try to find the invariance concept to keep track of the data. K minus 1 plus 1, what's that number? K minus 1 plus 1. Okay? K, right? K minus 2 plus 2, what's that number? Also K. Can we treat that K as the invariance? Yeah. When you go through all the equations, we should have this property, right? Every equation, if g of k minus t plus t, right? So here, we want to put a g of 1 here. What's that question mark? Sum of the two numbers should be k.
Minus k minus 1.
Yes, k minus 1. Because the sum of two numbers must be k, the invariance number. All right? Yeah? So here, invariance, size plus that constant term, equals k. Yeah. So,
Are we defining k as a positive integer?
yes, k positive integer. Yeah. But here, that's a question. Yeah. Let's delay that question. Yeah. K. Yeah. So k positive. Here we assume positive integer. Yeah. K positive integer. Yeah. All right. Yeah. So your expression. So g of k equals k minus 1/2. Yeah. Because this g of 1 is 1/2. Yeah. K minus 1/2. Yeah. So let's go back to the t function. Yeah. T function here. Yeah. Here equals k minus 1/2. So t of 2 to the k equals big parenthesis k minus 1/2 times 2 to the k. But we need to go back to the n representation. Not using k, using n. Yeah. 2 to the k, that's n. 2 to the k, that's n. So k equals log base 2 of n. Now you're concerned because for arbitrary positive integer n, your k may not be integer here. Okay? K may not be integer here. Yeah. Yeah. But here, think about, we are doing estimate, right? Yeah. So we don't require integer representation. We do estimate. Okay? Estimate, we keep it. We keep the non-integer expression. We do not need to use floor function, ceiling function to make it integer because it's an estimate formula, not an accurate formula. An accurate formula, you need to convert to floor function, ceiling function, make it integer. Here, we don't need it. Okay? It's estimate. Yeah. All right. So the final estimate formula, t of n, approximately equal to n times log of n. N log n. So here, Lg, remember Lg means the log base 2. In computer science, Lg means log base 2. In math, Lg means log base 10. Yeah. Based on what book you are reading. If you read a math book, log base 10. If you read the computer science books, you use log base 2. Yeah. All right. Here you can see we use the power of 2, we get an estimate. Then for the general case, we can still use the same approximation, the general term. Okay, same approximation. Yeah. All right. But so here, let me see. Yeah, how much time I have. Yeah. Yeah. So here, yeah, I didn't talk about the recursion tree idea. Actually, yeah, let me delay this recursion tree idea. Because when we learn quicksort, we will do the same thing again. Yeah. Quicksort, when we estimate efficiency operation, we get a similar recurrence relation. Yeah. But for quicksort, it's the best case. For the merge sort, this is the worst case. Quicksort, for its best case, we get pretty much same recurrence relation. Let me use the recursion tree estimate method in the quicksort place.
So are we approximating the quantity k minus 1/2 as a log of n?
No, yeah, k very close to log n, right? Yeah, that's good enough. So in our estimate, that's a good estimate. K minus 1, very close to log n. Yeah. Good estimate. Yeah. Because remember, when we use the asymptotic notation. Yeah. So when we use the asymptotic notation, okay, n or big theta of log n, usually we consider very large n, right? Large n, you minus 1, we don't worry about minus 1, right? Yeah, it's a small number. Yeah, yeah. So we can ignore minor terms. Yeah, so we don't worry about minus 1. Okay? So we feel very comfortable. We throw away minus 1. Yeah. So for k minus 1, k minus 1 half, so we feel very comfortable throwing away that little constant difference. Okay? Yeah. All right. Yeah. Yeah. So here, what I want to say, yeah, because in order to save time, yeah, yeah, because based on my plan, I need to, yeah. So here, based on my plan, I need to show you the recursion tree method. Recursion tree method. Okay, yeah. But in quicksort, later in our quicksort, we need to do this same thing again. Okay, why we just combine the two? Okay, yeah. I only do it once, yeah, to save, save some time. Okay, yeah. So let's delay this recursion tree method in our Wednesday lecture. Yeah. All right. So I finished part E, merge sort. So after this discussion, all right. So you get the whole merge sort. How to do the merge sort? Yeah. And the conclusion. Yeah. Conclusion. This one. The worst case, remember, the worst case efficiency of merge sort. Big theta of n log n. Big theta of n log n. See, can you see it's much better than all the previous three sorting algorithms? Previous three sorting algorithm, the worst case, the previous three, okay, worst case, all big theta of n squared. Here we get a big theta of n log n. Yeah. Yeah. So the most important property for the merge sort, its worst case is under control. Yeah. Or we can say in another way, we can avoid poor worst case. We can, by the worst case, we can avoid very poor worst case. Yeah. N squared we treat as poor worst case. Okay? Yeah, n squared, big theta of n squared, yeah, we treat as poor worst case. Yeah. N log n we treat as a good worst case. Very good, excellent, excellent. Yeah. Why? Because later you will see, even for the best, even for the average case, n log n is the best we can do. Average case, because average case, when you put the worst case under control, like the merge sort, average case is not far away from this worst case. Okay, yeah, yeah. So average case, worst case. Yeah. The best you can do is n log n. Yeah, yeah. Let's say in this way, for the worst case. Our part F, part E, part F. Part F, I will show you, nobody can do better for the worst case than n log n. N log n is the best people can do for the worst case. Okay? Yeah. Best people can do for the worst case. Yeah. All right, so let's take a break. Yeah. After you come back, let's do part F.